Hi everybody, I'm Louise Schoneveld and I'm going to talk to you about new indicator minerals, namely complexly zoned pyroxene as a fertility indicator for magmatic nickel-copper sulfide deposits.
To make a nickel-copper magmatic sulfide deposit, you first need a magma conduit, where mafic or ultramafic magma is entering into the system. You need to saturate this magma with sulfide, which is thought to happen via the incorporation of sulfidic sediments. This allows for sulfide droplets to form, which interact with the melt, enriching themselves in the chalcophile elements, and finally, to make this an economic deposit, these sulfides need to be deposited together in a trap. Our indicator minerals will have a unique chemistry depending on any one of these three processes.
The reason we need more fertility indicators is that the mafic-ultramafic intrusions that host these deposits are extremely common around the world, but very few of them contain sulfide, and even fewer still contain economically viable nickel-copper sulfides. So if we can focus our energy on more promising targets in the early drilling, we can save ourselves both time and money. The technique I'm going to be talking about for most of this presentation is X-ray fluorescent mapping. This technique gives us both textural and chemical information on quite large samples. It also requires very little sample preparation, with just a cut flat face as a minimum. It's also relatively fast, with roughly an hour per thin section to be mapped and roughly a day for the largest of the samples that fit in the machine.
So the new fertility indicator we'll be walking through today is complexly zoned pyroxene, which have been commonly observed in nickel-copper sulfide deposits. Here we have an example of a complexly zoned clinopyroxene from the Ritki deposit in the Fertility nickel belt in Finland. Most of the zonation is attributed to differences in the chromium content. Chromium diffuses extremely slowly in magmatic temperatures, which makes it an ideal indicator for magmatic histories. The types of zonation pattern can tell us a story about what's going on in the magma chamber. The most common type of zoning is normal zoning, which is enrichment in the core of the compatible elements and a depletion in the rims. These rims are often also enriched in the incompatible elements. This is just a normal reaction with the trapped liquid as the system solidifies. The next type of zoning is sector zoning, which is characterized by this bow tie or hourglass shape. This is an indicator of rapid growth of the pyroxene crystal. The next is an abrupt change from the cores to the rims, where the cores are highly enriched in chromium and the rims are very poor in chromium, which represents a rapid change in the system. And finally, we have oscillatory zoning, which represents a cyclic change during the crystallization of this pyroxene. When we refer to complex zoning, it's any combination of sector zoning, abrupt zoning, and oscillatory zoning within a single grain.
So the mineralized intrusions are characterized by mostly abrupt and sector zoned pyroxenes, both orthopyroxene and clinopyroxene, and can have oscillations throughout the grain and very commonly have olivine inclusions. So this is an example of an orthopyroxene from the Nintaka Hill deposit in Tanzania. What we're looking at is a stacked image where chromium is in red, iron is in green, and calcium is in blue. So the orthopyroxenes show up as oranges, the olivines show up as greens, and spinels are bright red. You can see that this grain has an abrupt zonation from the chromium-rich core to the chromium-poor rims. There's also oscillations throughout the center of the grain, and there's actually a sector zone in here. And finally, this is the Ritki deposit from the Fertility nickel belt in Finland. So this is an orthopyroxene that shows an abrupt zonation from the cores to the rims with fine scale oscillations throughout the rim of the orthopyroxene. From these XRF images, you can also get semi-quantitative chemistries. So looking at the cores of all of these crystals, most of them range between 4,000 and 8,000 ppm of chromium in both orthopyroxenes and clinopyroxenes. And then when we have an abrupt change, the rims of the clinopyroxenes and orthopyroxenes are usually between 2,000 and 0 ppm chromium. So here's a little montage of everything that we've looked at, and you can see that complexly zoned pyroxenes are very common throughout all mineralized intrusions. So looking at the pyroxenes in the barren intrusions, you can see most of them are quite diffuse in nature of their zoning patterns, where the cores are quite rich, but the change between the cores and the rims is very diffuse or non-existent. This leaves us with the question of why there is complex zoning associated with mineralized intrusions and not with barren intrusions.
Going back to our example from the Fertility nickel belt, this clinopyroxene crystal is complexly zoned, allowing us to determine that there was fast growth in the system, an abrupt change in magma chemistry, and then further small cyclic changes in chemistry, which all points to us having a very active system. Such would be found in a conduit type system.
So as the mafic ultramafic magma flows through the conduit, we have crystallization of olivine and chromite. It then flows through where the roof and floor have been incorporated into the conduit and begin to melt, which gives free silica, which allows for the crystallization of orthopyroxene and clinopyroxene oikocrysts. These oikocrysts then flow through the turbulent magma, interacting with variations in the chemistry throughout the conduit, and then finally settle to where they will crystallize and give usual trapped liquid reactions in the final solidification process. So what these complexly zoned pyroxenes are likely indicating is that we have a conduit type system rather than sulfides themselves. But because sulfides need conduit systems, this is a good indicator that you're looking in the right place. So using pyroxene as a fertility indicator would be a good option because XRF technology is becoming more widely available and becoming more advanced. So even though the images that I've been showing you are Australian synchrotron imagery, you can see abrupt zonation and oscillatory zonation in just a normal desktop XRF. And if you know what you're looking for, you could maybe see it in plain polarized light in some samples as well, just from a regular thin section. However, admittedly, our desktop XRF is a little bit out of date now, and over the last few years, the technique has become much more advanced, allowing for better resolution and better detection limits. So I have no doubt if your machine was a little bit more recent than ours, you'd be able to see a lot more features. So the main question we have remaining is how far this zonation extends from the sulfide. So far we've looked at the binary case of pyroxenes that are located directly near sulfides in mineralized intrusions and pyroxenes that are from intrusions that contain no sulfides at all. But ideally, for this fertility indicator to be viable, we'd need to know that these complexly zoned pyroxenes extend through the conduit away from the sulfides themselves, so they are a useful indication that you're looking in the right intrusion.
Thank you for watching this presentation. This was not a solo effort, it was a large collaborative effort from everyone who provided us samples and expertise, and of course the help of our wonderful discovery program here at CSIRO. This study was recently published as an open access journal article, so if you want to zap the little QR code on the screen, it'll take you to that article. Otherwise, feel free to contact me if you have any questions. Thank you so much, and goodbye.